like these contour maps. If you look at a contour map, we talked about this last time. Contour map, works where each of these lines represents like an elevation. So maybe this is like sea level, 0 feet off the ground. This is like 10 feet. This is like 20. This is like 30, right? Then if you walk around a contour line, you never change altitude, do you? If you walk perpendicular to a contour line, you're walking in the direction of the gradient vector. That's what you're doing. And if you follow there's an infinite number of contour lines. We only show some of them. But if you follow all of the gradient vectors throughout the entire picture, then you'd start maybe down here. It would take you through, and it would take you up to the top of the hill. And that would actually be the shortest path up that hill, because it's the steepest descent. Right? Yes?
Can you explain one more time how we've done that for?
I'm just looking at this angle right here, relative to the x-axis. This is 1, -1. This is that vector. Yeah. Yeah, just using the fact that it's, triangle 1, 1. Yeah. So let's just say, just for the sake of demonstration, okay? Let's just say that we would have got something like this. This ought to be good. What if we got a gradient vector of -4, -7? What would the angle be? So you'd come over here, you'd be at -4, -7. You'd be down here, right? So you could make a triangle, couldn't you? You could make a triangle out of that. It would look like this. -4, -7. You're trying to find an angle here. So what would you do? Arctangent. You'd use the arctangent on your calculator. It's the arctangent of the y coordinate over the x coordinate. What would you get? Did you try it?
Yeah.
What did it spit out? 60.25 degrees. So if you do arctan on your calculator of -4 over -7, what was it again? 60 point what? Oh, I just drew it wrong. -4 here and -7. Thank you. Yeah. Is that what you had done?
Yeah.
Okay, so what is it? 68?
No,
60.25 degrees. Is that the correct answer?
No.
No, because that's actually just this angle. Your calculator doesn't know you're in the third quadrant. So you'd have to add 180 to that to put you over there. So you'd be a little careful with that. That would be, that's stuff from pre-cal though. We always have to be careful with that inverse function on the calculator, right? Those darn domain restrictions mess everything up. This problem is very similar to the one we just did. I think this one might be a little easier. Well, that's exactly the same, isn't it? Same instructions?
Yeah.
Okay, so I'll let you do that on your own. I think that partials are easier on that one. Yeah? Ooh, now that one. Let's see about this one. Here's a function of 3 variables. Find the directional derivative at this point in this direction. So this is what we started class with. Directional derivative, I give you a vector. You've got to go through and make sure first that this is a unit vector, right? And then go through the whole computation. Then it says to find the magnitude of the gradient at the same point. So this directional derivative is giving you some instantaneous rate of change at that point, right? If we're pointing in a certain direction. This is also giving you an instantaneous rate of change at that same point. Which of those is going to be larger, A or B? B, it has to be. The gradient's always the biggest rate of change you're going to get. The magnitude of the gradient is always the biggest rate of change you're ever going to get. So, do you want me to work this? Yes? Okay. So let's do part A. I'm going to make this a little smaller. Or you know what? I'll go like this. There. So for part A, I need the directional derivative, right? The directional derivative in the direction of v of f of x, y, z should be equal to, why am I using this marker? Should be equal to a times the partial of f with respect to x at x, y, z plus b times partial of f with respect to y at x, y, z plus c times partial of f with respect to z at x, y, z. That's just the definition of the directional derivative. What are a, b, and c? Is it 1, 2, negative 1? No, that's not a unit vector. This is not a unit vector, is it? I have to make it a unit vector first, or else it's all going to be off. So what is the length of that vector? Root 6. So if I take this and I'll call it u. How about that? I'll just scale this 1 over root 6, 2 over root 6, negative 1 over root 6. Now that's a unit vector that points in the same direction as v. And so I should come over here and not call this v anymore, right? I should call this u. I was doing that intentionally. I wanted you to accidentally stumble into that, to remind you, you must make it a unit vector. Then I need partials. Are we going to do partials on that? That's going to be pretty easy, I think, hopefully. Let's see. Let's go ahead and start writing this down. A is 1 over root 6. And partial of f with respect to x is sine yz. Then I have plus b, which is 2 over root 6. And then partial of f with respect to y, which is x cosine yz times z. Right? Ignore the x, because it's a constant. What's derivative of sine of yz? Cosine yz. Then derivative of what's inside with respect to y? Z. So it's actually going to be xz cosine yz. Plus c, which is minus, so minus 1 over root 6. And now the derivative of this with respect to z. So xy cosine yz. Good. And now I'm going to plug in 130, right? So the directional derivative in the direction of u of the function at 130 is 1 over root 6 sine of, yes, sine of 0, right? Because z is 0. That's all gone, isn't it? Plus 2 over root 6. Yes, 0 again. Minus 1 over root 6. Right, this one's 0 because z is 0, right? Okay. This one, not so much, right? And so 1 times y, which is 3. Cosine of 0 is 1. So 1. So this is just going to be negative 3 over root 6. Questions? No? Okay. Part B. What's the magnitude of the gradient vector at 130? Well, we know what the gradient vector is, right? We actually got the partials already. So let me just write down what the gradient vector is.
Wait.
Whoa.
For
What did I miss?
for this one, xz cosine 0, or cosine yz, shouldn't it be 2 root 6 there? Oh, z was 0.
Z was 0.
Okay, never mind then.
That saves us. That saved me.
Got it.
Yep.
Wait, no.
No,
Wait, wait.
Thank you.
no, I've made mistakes before. Wouldn't be the first time. Okay, magnitude of the gradient. So the gradient vector, I just erased it. Absolutely wonderful. The gradient vector,
That's why I said wait.
yeah. What was it? X sine yz? So sine yz, right? And then it was yz, and then xy, cosine yz. So that's the gradient vector right there, right? And all I need to do now is plug in the point 130. The gradient at 130 turned out to just be, well, this was 0, right? And this one was 0. And this one turned out to be 3, right? That's not the magnitude of the gradient, that's just the gradient. I need its magnitude to find the maximum rate of change. So the magnitude of the gradient of f, and this one's an easy one to do, right? But square root of all that square is just 3. So it definitely has to be bigger than the other answer. If this answer is smaller than the other one, something's wrong. All right? Good? All right, so tangent planes to surfaces. This is the last part of this section. So we already know, we've been exposed to the concept of the tangent plane. We did this, right? And the idea was this, I'll remind you since it's been, oh no. Whoa. What we had before was this. We had that if z was equal to some function of x and y, that made a surface, right? That we could find the equation of the tangent plane to this surface using this formula. It was the partial of f with respect to x at x naught, y naught, x minus x naught, plus partial of y, f with respect to y at x naught, y naught, y minus y naught, minus 1, z minus z naught equals 0. Do you remember that? It just said that, look, the A, the B, and the C for the standard form of a plane, right? We had ABC. The ABC is the direction vector. That this A and B came from these partials. And the C, I told you, was always -1. Didn't I? But what we needed for this to work is that we needed Z to be a function of x and y so that you could draw a surface. Now what we're going to do is we're going to generalize this even further. Do y'all recall this? I mean, we did do this in class. We're going to generalize this formula, and this time we will no longer need the condition that you can solve for z. You no longer need that z is a function of x and y. Now you just have an equation, any equation that connects x, y, and z together. So if you give me an equation that's x, y, and z are all in the equation, then I can find the equation of the tangent plane to any point on that surface using this formula right here. Does it look familiar? Yes. Now, we've got 3 variables, right? X, y, and z. So you have to give me a point on the surface, x naught, y naught, z naught. Because this surface could possibly be like, an ellipsoid, a ball, like a sphere. So you could have points on the top and the bottom. It's no longer a function of x and y. So you have to give me exactly where you are on this surface. Give me that point, that's x naught, y naught, z naught. And then what I'm going to do is this part, and this part. That's that standard part of the equation of a plane that we've seen so many times before. X minus x naught, y minus y naught, z minus z naught, right? But these pieces are now a little different. Partial with respect to x, that's the way it was before, wasn't it? In the previous tangent plane equation. Partial with respect to y, that's what it was before. The difference, though, remember that was -1? No longer -1. It's this. It's the partial of, with respect to z. So this is the a, the b, and the c. So that's actually the normal vector of the plane. Remember the normal vector sticks out the plane like this? So the gradient vector is the normal vector of the plane. That's what it is. All right, let's see if we can do one of these. I've got a little bit of time. Find the equation of the tangent plane to this ellipsoid. Now, you may or may not recognize that as an ellipsoid. We talked about quadratic surfaces at some point in this class. We wanted to be able to recognize them. And I said, hey, let's not try and memorize them. Just remember, they're all on that one page, and you could look them up. But this is an ellipsoid. I'm telling you that. So you got this ellipsoid. Looks like an egg, right? And we're going to some point on it, wherever, -3, 4, 5, wherever that is. And we're trying to find the equation of the plane that is tangent to that ellipsoid. That's what we're doing. Got it? So what we're going to do is first take the equation, move everything to one side, which it almost already is. If this is a constant right here, you actually don't even need to move it over. It'll still work. And I think in the homework problem I did, I just didn't even move the constant over. The reason why it won't matter is because you're going to take a derivative of that, and that constant's always going to go away. This left side, though, of this equation is capital F of x, y, z. That's the thing we're going to take partials of. What part of the equation of the plane, what part of it can you tell me right now without doing any of the work?
X minus x.
You can tell me x minus x naught. So I know x minus x naught, so x plus 3. Then there's something, then it's what, y minus 4, and then I know it's z minus 5, and I know equals 0, right? That much I know. Just a matter of figuring out what these numbers are in front. Those numbers are the direction numbers of the normal vector, but that comes from the gradient. So just some partials now. What is the partial of capital F of x? Or sorry, the partial of capital F with respect to x would be, oh man, that's cake, right? 2/9 x. And partials don't get any easier than that, right? Well, I guess they could, but not much. Partial of f with respect to y would be 2y. Partial of f with respect to z, 2/25 z, right? Man, that's nice. And now what I need to do, this number right here, is a partial of f with respect to x with -3, 4, and 5 plugged into it, right? So plug in -3 for x, 4 for y, 5 for z. But it only has x in it, right? So all I have to do is plug in -3. Let's plug -3 in right there. What do you get? -2/3. So this is -2/3. Then I need to do this one, which is the partial with respect to y at the same point. Fortunately for us, this only has y in it. So I just plug in 4, and 4 times 2 is 8. So this is +8. You following? Last one?
2/5.
2/5. Voila. There it is. That's the equation of the plane. Now you could go through and clean that up, right? Distribute through. If you didn't like the fractions, you could multiply both sides by 15, and you could do whatever. I've seen on your homework, on your homework, I meant on your take-homes, I see some of you leave them, some of you clean them up. I don't care. It's all the same, right? It's all the same sheet of paper on, living in three-dimensional space. So, not bad, huh? Not bad? Questions? Questions? I've got something interesting to show you. No questions? I can erase?
Do you need it first?
Wait, hold on. Nope. Messing with me. We said that if z was a function of x and y, that the formula for this, for the equation of the tangent plane, right? We said the formula was partial of f with respect to x at x naught, y naught, times x minus x naught. Then it was plus partial of f with respect to y at x naught, y naught, y minus y naught. This is the second time I've written this on the board today. And then it was what? Minus 1, and then z minus z naught, right? Equals 0. That's what we said, right? And I just told you that, and you believed it and everything. And I told you it was always negative 1, right? It was always negative 1. I told you that. Okay, so what I'd like to do now is I'd like to imagine that this is an equation, right, that does involve x, y, and z, doesn't it? I mean, I'm not telling you what f of x, y is, but would you agree that we should have x, y's, and z's in that? I'm going to use the method we just did to prove that this formula is right. So what I'm going to do is move everything to one side first. And I actually think I'm going to bring the z this way. So this is 0 equals f of x, y minus z. Right? This right side is capital F. According to the formula, x minus x naught, I know. Y minus y naught, I know. Z minus z naught, I know, right? Equals 0. I just have to figure out what these pieces are. What is the partial of capital F with respect to x? Well, what's the partial of this with respect to x? Well, little f, partial of little f, right? With respect to x, that's what that is. Then you could say at the point, you could put here x naught, y naught. Z naught, I don't have to worry about. Why don't I have to worry about z naught into this piece right here? It just has x's and y's, right? There is no z in here. So this is just going to be partial of f with respect to x at x naught, y naught. And then minus what's the derivative of z with respect to x? 0. So that's it. Then I get to this piece. What's the partial of capital F with respect to y? Well, it's the partial of this with respect to y at x naught, y naught, right? Minus the partial of z with respect to y, which is 0. Okay, move on. Here, what's the partial of this with respect to z? It has no z's in it. That's a function of x and y, so it's 0. What's the partial of this with respect to z? Negative 1. There it is. So that formula actually came more from this one. Like the one I gave you just today did not come from that one. It was the other way around. That one comes from this one. No, that one comes from the previous note. Got it? Okay. One more thing to talk about. Was that the same problem? Yes, that's the same problem. Look at the directions. These are a little bit different than what we just did. Find the equation of the normal line to the tangent plane of the ellipsoid. So we have the same picture we just did a second ago. We had an ellipsoid. We picked a point. We found the tangent plane. And we got that, didn't we? We got the tangent plane. Now what we want is for you to take that plane, right there, okay? Take that plane and give me the equation of the line that is normal to the plane. Now what we mean by that is the line that is perpendicular to the plane, that pops out of the plane, normal meaning perpendicular. So what's the equation of this line? Well, what do you need for the equation of a line? A point and a direction vector. Do we have a point? Yes. Do we have a direction vector? What?
It was negative 2/3.
It's the normal vector of the plane, which is the gradient vector, right? So this is really just, once you've answered the previous problem, this problem falls out immediately from it. So we were trying to find the line that comes out of this thing perpendicular to that plane. That's what we're trying to find. This line that extends in both directions forever. That's called the normal line. So for that line, what do we use for lines? I forgot what we used for lines. RFT, thank you. RFT equals R naught plus TV. Remember that? R naught is a vector that you create from any point on the line, which we want the normal line to go through that point. So that's going to be -3, 4, and 5, plus t times v is the direction of the line, which we said is basically parallel to the normal of the plane. I forgot what the normal of the plane was.
Negative
2/3,
2/3.
8,
2/5.
2/5. That's just the a, b, and c from the equation of the plane. And then you could put those together, right? Put these two vectors together. I won't do it. We've done that before. You could then you could say, okay, this is the vector equation. You could be asked to write it as the parametric equations. You could be asked to write it as the symmetric equations. I believe that's the end. Oh, that's just a picture. There it is. That's the actual ellipsoid we were just looking at. I think my picture was actually better than this. Don't you think my picture's better than that one? I think it is. There we go. That's the homework. All right. Hey, a little bit of, I guess, a warning. I don't know if this is that's the right word. I get the sense that a lot of you are a little bogged down with all your other classes, and you're bogged down with these mini exams, and they're really you're focusing a lot of time and energy on them. And that's great. This midterm is going to be focused solely on homework problems. And so I get a sense that there are a lot of people who are just doing mini exams and aren't really touching the homework. And I just don't want that to come back and bite you, because you need to at least expose yourself to the types of problems that you're going to be asked on the test. So make sure you take some time to get yourself up to speed, caught up on all the homework assignments. You don't want that to be 11 o'clock the night before, right? That you're like, I'm just going to go back and review all this homework. The expectation is that you've been doing the homework and the mini exams. That's the expectation. So, yes?
Is the midterm going to be more like the mini exams or no?
I thought I just said that. Well, no, I just did. Did I not make that clear? I'll make it more clear. Just it's going to be over homework. I mean, that's what I'm concerned about. Is everyone's like, yeah, I've been kicking ass on these mini exams. I'm doing a good job, and I'm getting the hang of this. And then you get to the midterm, you're like, what the hell's this? Oh, that's the homework you were supposed to be doing. You don't remember seeing a problem like that? So focus on homework for midterm. Yes. Yeah, and examples that I do in class. Yeah, what you'll notice though is a lot of the examples that I do in class are just the concept. Okay, so like the problem we just did, like this tangent plane one. The partial derivatives were pretty easy. In the homework, they get a little bit tougher. And so, yes, I would say always go back and look at these notes, these examples. But also go to your homework and find okay, he did one like that in the notes. Here is that example in the homework, but harder. make sure you know how to do that. Any other questions? Okay, have a great weekend, right? It's Wednesday? Have a great weekend. Not really. Yeah, there's really not going to be a review for the test. It's just practice your homework. Yes. Huh? I haven't decided on that. Let's talk